All right, so the plan for today is to finish section 2.3 on limit laws or limit properties. We started that last time. So looking to finish that up today and then talk a little bit about 2.4, the precise definition of a limit. We're not going to go too deeply into this material, just kind of introducing the idea, showing you what precisely we mean when we talk about the limit. We kind of gave a hand wavy definition. And we'll look at going through some formal proofs of a couple of the limit properties and a particular limit. We'll see that it's fairly cumbersome to do, and it's not easy going. It's not as kind of procedural as a lot of the problems that we do in calculus. So this is more what we would call like an advanced calculus idea or real analysis, kind of a more theoretical course you would take after the calculus sequence if you were interested in that. This is really kind of towing the line of a course like that. But I think for some of the simpler properties, we can demonstrate the use of this formal definition of a limit and how it might work, and give you a little bit of a taste of that theoretical basis that underlies what we're discussing in the rest of chapter 2 and in much of the rest of Calc 1 through Calc 3. Note that the chapter 2 homework is now visible on WebAssign. I got an email yesterday that kind of made me aware that I had a setting marked incorrectly. I fixed that. You should be able to see the chapter 2 homework now, 2.1 through 2.8, on WebAssign, or I think 2.1 through 2.8, maybe just through 2.7. So you should see that now on WebAssign. I set 2.1 and 2.2, those homeworks to be due this coming Sunday. I think that's enough time to knock those out. And then 2.3 and 2.4, maybe 2.5 as well. I bump back to the following Sunday. So yeah, take a look on WebAssign. Those homeworks are available now. And our quote of the day for today is, this is a paraphrase of something that Ralph Waldo Emerson wrote. And this kind of tends to happen with quotes when somebody makes a quote that has kind of an interesting idea to it. Over the years, it kind of becomes streamlined a little bit. And I like this version of it. What you do speaks so loudly that I cannot hear what you say. It's kind of like actions speak louder than words, but really kind of to the nth degree that actions speak so much louder than words that if your words are discordant with your actions, the words kind of aren't even heard. And I think an interesting question to ask yourself from time to time, and I do this as well, or at least I try to. If you had to write say a paragraph, for, I don't know, an English course or something, and they said, what things in your life do you value most? Oh, I should value spelling more, apparently. What things do you value most? Um, things like family or health or friendships, or there might be a lot of different things that people come up with. And then if you ask the second question, okay, if you look through, the past week, the past month, if you look at your credit card statements, if you look at your time expenditure, what you spend your resources on, your time, talent, and treasure, so to speak, what does that spend look like? And is that spend concordant with the things that say that you value? And I think this is less of a like worry that, oh, maybe people looking at me you know, will think that I'm a hypocrite or something. It's more of just kind of an internal check, because I think especially these days we have so many things all pulling at us, with such a fast-paced culture. It's super easy to get sucked into Facebook or TikTok or YouTube or Instagram or whatever, and 3 hours later you come out of it and it's like, what did I just spend all that time doing? Um, and if that happens once in a while, no big deal. But, is that happening so much that you don't have time uh, to really put forward the things that you value most in your life? And um, yeah, so I think that is an important question to kind of ask yourself every once in a while. You know, what is important to me? If I had to write down like a life mission statement, what would it be? And is the expenditure of my time, talent, and treasure kind of in line with what's important to me? As students, maybe getting good grades is quite important to you, or setting yourself up for a good career path. Is things like going out with friends getting in the way of that, right? Now, you don't want to not go out with friends at all. You have to balance everything, but kind of everything in moderation. Okay, so moving on to the material. So just a quick reminder of the last couple of class meetings. We had discussed the limit of a function, section 2.2, which I'm for some reason having trouble selecting here. And as part of 2.2, my computer is running really slowly. Maybe I have to close something. But as part of 2.2, we introduced the definition of the limit. And I mean, we gave a definition. It's not a precise definition. So, you know, a mathematician might balk at calling this a definition, but this is the idea or the notion of a limit, is that we can make the output of a function as close as we like to the proposed limit L by taking the values of the input x sufficiently close to, but not equal to, a, the limiting value. And we said, okay, we have some limit laws as well, some properties of limits. We investigated coming up with limits basically by looking at tables or pictures and making an educated guess pretty much. Can we formalize that process? Can we come up with some theorems, some helpful properties that we can apply algebraically and be certain that this number that I get at the end is actually the limit? It's not just an educated guess, or it's not something that might be off by 10 to the minus 5, but can we be actually sure that that is actually the limit? And these were a list of properties. We had the linearity properties, limits split sums apart and constants can come out. The limit of the products, the product of the limits, being very careful that this does not generalize to some of the other important ideas in calculus like derivatives and integrals. They don't split products apart the same way, but they do have these two properties. The limit of a function to a power, you can move the limit inside the power. The limit of a constant is just that constant, or in other words, the limit of a constant function, a function who for any input gives the same value as the output. It's just that constant output that is the limit of the function. The limit as x goes to a of x is a, and the limit as x goes to a of x to the n is a to the n. And we also had a corollary that if f is a polynomial or if it's a rational expression where a is in its domain, then we can do the kind of plug-in thing that we were really tempted to do in section 2.2. We noticed that often when we were looking at a limit x goes to f of x, the result often turned out to be f of a. But we had enough cases, I think, where the limit didn't turn out to be f of a, either something different or it turned out to not exist. Or we had situations where f of a doesn't exist, but the limit does exist. So hopefully we had enough counterexamples that we're cautious and we don't just want to go and try the plug-in thing and see what happens. But if f is a polynomial or if it's a rational expression where a is in its domain, then the kind of plug-in operation does work. We can just plug the a into the function f, evaluate it, and that's the value of the limit. And as an exercise, I gave you this limit to work through. We did one that was pretty similar to it. And I think that's where we'll pick up today. We'll work through this one. We'll go through some additional exercises and examples, and then look at section 4. All right, so if I look at this function, t to the fourth minus 1 over t cubed minus 1, I do note that it's a rational expression. However, my limiting input, t goes to 1, that's not in the domain of that rational expression. Why? Because, well, 1 cubed minus 1 is 0. I get a 0 on the bottom. That's not in the domain of the rational expression. Now, we might look at this and think, oh, okay, I get it divided by 0. Maybe like my limit's infinity or doesn't exist. We might jump to a conclusion like that, but that would be premature. We don't want to just automatically say, because if I plug in, something blows up, then the limit doesn't exist. Well, we're not allowed to plug in that case. So we need to do something else. We need to think of a different way to approach this problem. Now, in this instance, I realized that kind of if I hypothetically were to do the plug-in on the top, I get a 0, and on the bottom, I get a 0. So I'm not, officially doing this, but I'm thinking, what would happen if I did this? I get a 0 over 0. We talked about last time, that's called an indeterminate form. And given that my numerator and denominator are both polynomials, that means that 1 is a 0 of the numerator polynomial and of the denominator polynomial. That clues me into the fact that a t minus 1 should factor out of both the top and the bottom. Now, why is that important? Well, if a t minus 1 factors out of both, I can divide them out, and that might get rid of whatever's causing this 0 to pop up in the denominator. Why can I do this? Well, implicit in the limit is t being not equal to 1. T is going to 1, but not equal to 1. Now my numerator, t to the fourth minus 1, factors into t squared minus 1, t squared plus 1. And t squared minus 1 factors into t minus 1, t plus 1. In my denominator, I have t cubed minus 1. Again, I know that a t minus 1 is going to factor out because if I plug in 1, I get an output of 0. And you might remember the formula for difference of two cubes, or for sum of two cubes, the factoring formula. They're pretty similar. I don't memorize it. I just remember how to get it. I know that I'm going to have I'm going to have three terms here in my remaining quadratic. The first term, I want to multiply by t and get t cubed. That's got to be a t squared. The last term, the third term, I want to multiply by minus 1 and get minus 1. That's got to be a plus 1. And then I have this cross term, or this middle term. This middle term is going to have to eliminate the extra kind of vestigial pieces that I got out. So if I multiply t squared by t, I get a t cubed, which I want to keep. But then that t squared also multiplies the negative 1, giving me a negative t squared. I want to get rid of this. The plus 1 multiplies the minus 1, giving me a minus 1, which I want to keep. But it also multiplies the t to give me a plus t, which I need to get rid of. So what can I stick in the middle here to get rid of a plus t and a minus t squared? If I do maybe a plus t, that plus t is going to hit the minus 1, giving me a minus t. That plus t is going to hit the t, giving me a plus t squared. And they both go away. Everything works out nicely. There's so many minuses and pluses floating around in these summer difference of two cubes that I prefer to just do it this way. Once you do it a few times, it goes a lot faster than doing it with me talking through every step. But I do notice that my t minus 1s divide out. Again, remember the domain restriction t not equal to 1 coming from this, the existence of this limit. Now if I look at limit t goes to 1 of t squared plus 1 times t plus 1 over t squared plus t plus 1. Again, I have a rational expression. It's a slightly different rational expression. Now, if I plug t equals 1 in the denominator, well, I get 1 plus 1 plus 1. That's just 3. That's not a 0. 1 is in the domain of this rational expression. This one that's pretty similar to the previous one, but has that minor difference in the domain restriction. Here, I can just plug in 1 to get what? 1 plus 1 is 2, times 1 plus 1 is 2, over 3, or 4/3. Any questions so far? My OneNote is going really slow. So let me close a couple of windows over here. I'm gonna close a couple other things I have open, and hopefully that makes OneNote speed up a little bit. Okay. My handwriting is already not not the best. So um there we go. All right, so the answer to this one was 4/3. Hopefully you worked through that exercise and you found that an exercise related to I think the last problem we did last time with the multiplying by the conjugate kind of idea. Uh, you can work through this one after class, try to compute this limit. Again, we see that if we like thought about doing the plug-in thing, we really don't have any suspicion that it should work here because this is not a rational expression. It just has square roots all over it. But if we kind of just tried to force the issue just to see what happens, we see we get square root of 1 minus square root of 1 is 0 on the top and 0 on the bottom. We eventually want to work our way to something where I can divide out a t from the top and the bottom and get something where I can use my, maybe use several of my properties from that list to work my way to an answer. So as an exercise, work through this problem. Okay, we're going to look at another problem here. Here we have limit h goes to 0 of 1 over h minus 1 over h squared plus h. I do have kind of two rational expressions here, difference of two rational expressions. I might think of this as like limit h goes to 0, 1 over h minus limit h goes to 0 of 1 over h squared plus h. Might be tempted to do that. But remember that property of like splitting up sums or bringing constants out, which we're kind of doing those two things in conjunction if we split up a subtraction. That really only applies if my resulting two limits are both real numbers. They both exist, they're both real numbers. So what do I think about, for instance, limit h goes to 0 of 1 over h? We can get an idea looking at a picture. As h goes to 0 from the right, I see that my output of my function gets larger and larger. It looks like the right-hand limit is infinity, and it looks like the left-hand limit coming from below is negative infinity. So actually, this limit doesn't exist. Or if it kind of did exist, if I was just looking at, say, one direction, if I was maybe just looking at the right-hand side, the limit would be infinity, and that's not a real number. So I don't want to try the splitting sums or differences apart. I don't think that's going to be the right strategy here. That property doesn't apply in this case. If I did try to kind of force the issue and just see like, what do I think would happen? I would get something that looks like infinity minus infinity. Because the second bit, the 1 over h squared plus h, that's kind of doing a similar thing. Infinity minus infinity is another kind of indeterminate form. So infinity minus infinity, something that has that form, the limit could be 0, it could be infinity, it could be negative infinity, it could be 12, it could really be anything. So we see that we get an indeterminate form here. The limit could not exist as well. That's another important possibility. I do notice that I have the difference of two rational expressions here. Maybe I can combine them into a single rational expression and clean things up a little bit. Maybe I get a little bit more clarity that way. I know the rational expressions are a little easier to work with than more complicated functions like this one. Now the denominator of my second term, h squared plus h, is just h times h plus 1. And my first term just needs an h plus 1 on the top and the bottom to get a common denominator and minus 1. I see I get h plus 1 minus 1 is just h on the top. The h and the h divide out. And this is what I'm left with. Why do I not have to be careful when I divide out the h's? You know, it seems like I previously had a domain restriction that h couldn't be 0, and now I've lost that restriction. But again, remember that because we're operating under the limit, h is not allowed to be 0. If I plug in h equals 0 now, which I now can do because I have a rational expression where 0 is in its domain, I get 1 over 0 plus 1, or just 1. Any questions so far? I'm going to close a couple more windows here. OneNote was behaving nicely for a couple minutes there, and then uh, not so nicely. I think I found the issue. I have one window that doesn't seem to be responding. Let me close that. It's another OneNote window, so it might close the one that we have open right now, but okay, I think that was the one that was giving me some trouble. It closed everything else but that one. All right. So any questions on any of this so far? All right. Oops, need a little more space between these. Okay, so let's look at the next example. Given some value of x, we're just taking x to be a constant here, some real number that's not 0. Compute this limit. Limit h goes to 0 of, in the numerator, 1 over x plus h squared minus 1 over x squared, all divided by, in the denominator, h. When we're inside of a limit, we're kind of thinking of the variable that the limit is operating on h being kind of the variable and anything else kind of being a constant. So we're just basically treating x like a constant here. H varies, it's getting closer and closer and closer to 0, but x is just kind of whatever it is, some non-zero number. We have taken 0 out of contention for the value of x. Again, if I just this is a rational expression in h. It's a complicated looking rational expression, but it could be boiled down to a rational expression. If I just plug in h equals 0, what am I going to get? I'm going to get a 1 over x squared minus 1 over x squared on top. That's 0. And on the bottom, I'm also going to get a 0. So I get a 0 over 0. That's a familiar indeterminate form. And I kind of know what my strategy is. My strategy is to do some algebra to try to get an h in the numerator, a factor of h in the numerator, a factor of h in the denominator that I can cancel, I can divide out. And then hopefully get a rational expression where I've gotten rid of that issue with the domain. And then I can plug in h equals 0. So that's kind of my goal. Let's see if we can do that. In my numerator, I see I'll have a common denominator of x squared times x plus h squared. That's going to mesh with my denominator of h. So I have h x squared, x plus h squared. That's all going to be a denominator. And then to get my common denominator in the numerator, I'm going to get a factor of x squared on the first one and a factor of x plus h squared on the second term. Uh, part of being good at Calc 1 is being good at algebra and pre-calc. So things like this, you might not have seen where all of those steps come from. If you didn't, that's perfectly fine. But go through your notes afterwards and fill in all of these blanks. Make sure that you understand exactly what steps I took to get from the first statement to the second statement. Um, and if you're struggling with that, go and do some practice problems on Khan Academy or Math TV, something like that. Practice problems from the book from chapter one. Um, drill some of this if you come across a topic that you're not familiar with, especially in Calc 1, but this also applies to Calc 2 or Calc 3 or really any future math course. It really kind of stinks to like be really good at the calculus and then sit down and take an exam and lose a letter grade or two because you messed up a whole bunch of algebra. And that's a very real possibility. So make sure that you're super solid on these algebra fundamentals. Um, not only does it help you understand the calculus material, but also when you're actually solving a calc problem, you're going to always be using those algebra fundamentals as well. So if there's a weak point that you come across, go back, take the time, strengthen that up. Uh, and then that can be a strength from that point on. Okay, now this numerator, be careful with my sign here. So I have a minus applying to this whole quadratic term. So minus x squared minus 2xh minus h squared. I see my x squared minus x squared goes away. Everything that's left over in the numerator has at least one factor of h that we can divide out with that h in the denominator. So I have minus 2x minus h over the h in the denominator went away over x squared times x plus h squared. And then lastly, we look at this and we say, is h equals 0 in the domain of this rational expression? This is some other rational expression in h. And the answer is basically, well, the answer is yes, right? One little side note, it might kind of irk us that we have this kind of x plus h here. What if h turned out to be negative x? Well, that would be dividing by 0. Now, we're not letting x be 0. So as h heads to 0, eventually h will be, say, for instance, smaller than x over 2 in magnitude. So eventually, as h gets closer and closer to 0, say absolute value of h will be less than, say, absolute value of x over 2. So then we don't ever have to worry about h being like equal to negative x. We can restrict ourselves to, if needed, a super small open interval surrounding 0 that we let the h operate in. And we can stay away from any issues with, say, h being equal to negative x. So that's a technical little detail, but it's important for us to realize that we can do that kind of a thing. The only value of x we couldn't, stay away from in h would be x equals 0, but we've specifically excluded that possibility. So whatever this rational expression is, whatever value of x we're working with here that's not 0, h equals 0 will be in the domain of the rational expression as a function of h. And therefore, our corollary applies. We can just plug in h equals 0 and get negative 2x over, well, x squared times x squared is x to the fourth, or negative 2 over x cubed. Any questions on this one? So the algebraic steps on this one were maybe a little more challenging than some of the previous ones. We also had this little technical detail with this x plus h bit here and being able to restrict ourselves to as small an open interval as we like about 0. But I think the overall strategy kind of should feel the same as the strategy for our simpler problems. All right, and then last example in this section, let's look at the limit x goes to 0 of 1 over x minus 1 over absolute value of x. So here I have an absolute value, and if I want to do any algebra with this, I pretty much need to get rid of that absolute value. So how do I get rid of an absolute value? Well, the kind of general strategy is to look at different cases. So you look at maybe one case where the inside of the absolute value is positive, see what happens there. Look at another case where the inside of the absolute value is negative, see what happens there. Okay, so let's consider, say, the case where the absolute value is positive. Or sorry, where the inside of the absolute value is positive. Well, that's where x is bigger than 0. Well, that's just the right-hand limit. So let's investigate the right-hand limit of this function. Well, when x is bigger than 0, when x is a strictly positive number, absolute value of x is just the same as x. The absolute values just kind of go away. Now, something very important here. We might look at this and say, oh, this is like, I don't know, infinity minus infinity or something like that. Or we might think that it's equal to infinity or that it doesn't exist. But something really important is that we're picking specific values of x as x goes to 0 from above, specific positive values of x, like x equals 1 or 0.5 or 0.1. So being able to think back, at least abstractly, to that table kind of model that we were using before, or the graphical model, is really important. If I pick x equals 1, I get 1 minus 1 half, I get 2 minus 2 is 0. X equals 0.1, I get 10 minus 10 is 0. Every single positive input into this thing here gives me exactly 0. I get thing minus itself is exactly 0. Now, if I tried to plug in 0, I'd have a big problem. I wouldn't really know what to do. But remember, the limit is excluding that possibility. I'm not allowed to plug in 0. I'm only plugging in strictly positive numbers. When I plug in any strictly positive number into this function, I get exactly 0. This is limit as x goes to 0 from above of the 0 function. For whatever input I put in, I get out 0. And that's, of course, just 0. Okay, so my right-hand limit, my limit from above, is 0. If I look at my limit from below, if I look at my left-hand limit, and if it exists and is also 0, then my overall limit is 0. If it exists and is something other than 0, or if it doesn't exist, then my overall limit doesn't exist. So let's investigate the left-hand limit. Limit x goes to 0 from below of 1 over x minus 1 over absolute x. And once again, I want to get rid of the absolute values, but here I know that the absolute value of a negative number is negative of the input, right? So when we're plugging in only strictly negative numbers, absolute value of x equals negative x, right? How do I make a negative number positive? I take its negative. So now I have a minus 1 over negative x, or a plus 1 over x. Well, now if I plug in negative numbers, like say x equals -1, I get -1 plus a -1. that's -2. That's not 0. If I plug in a number like -0.1, I get -10 minus 10, that's -20. Well, this is really just limit x goes to 0 from the left of 2 over x, right? 2 times 1 over x. And that, just quickly drawing a little schematic here, as we're approaching 0 from below, clearly this is yielding outputs that are heading toward -infinity. I can make 2 over x as large negative as I like by choosing values of x strictly less than 0, but that are sufficiently close to 0. Therefore, that limit is -infinity. The limit from the right is 0. The limit from the left is -infinity. The overall limit does not exist. Any questions so far? Give me 1 second here to, my OneNote is still acting up, so I want to actually close it completely and then restart it. And I'm hoping that that will help things a little bit. Every once in a while, my computer just like does not want to run OneNote right, and I'm not exactly sure why.
I can tell you, I was on Zoom last night and my computer was for some reason lagging really weirdly, just like you're describing. It
Oh
made me
yeah.
want to Zoom. I'm not sure why, but I noticed that when I was on a Zoom call last night.
Yeah, yeah, it's like 95% of the time the tech works great, but I think the other monitor might have something to do with it too. I'm not really sure. Yeah, and unfortunately, like I just brought it back up and it didn't save any of the work that I just did. So, um, which isn't a big deal. I mean, we made it through these problems, but let's see. Yeah, Zoom seems to be one of the buggier Microsoft programs, which isn't saying a whole lot because Microsoft programs tend to be a bit buggy to start with. Or wait, did I say Zoom? OneNote. I don't know if I said Zoom or OneNote tends to be the buggier program, but OneNote tends to be pretty buggy.
Zoom's not the greatest either.
Yeah, yeah, yeah. You can see that it like actually just all of the stuff that I was writing for some reason didn't record when I closed it. So, which is not a big deal at all. I just use this as kind of a whiteboard, but um, all right. So now hopefully we've got a fresh opening of OneNote. I'm not going to go as far as to shut down the whole computer or anything. That would be way too disruptive, but we should be good for the rest of today, hopefully. The other possibility is that I might just have too many math equations written on here. That does tend to lag some Microsoft products. I haven't noticed it too much recently, but it used to lag Word really bad if you got past, 2 or 3 pages with like quite a bit of math formulas from the equation editor on it. So that could be the issue too. But fingers crossed that we're good now. Okay, so we just worked through these two. Unfortunately, don't have the work, but are there any questions on anything up to this point? So again, it's tempting to just do the plugin thing all the time. Don't do that unless you have really good reason to, unless that corollary applies. Polynomial or rational expression where the thing you'd be plugging in is in the domain. But you can use the kind of plugin idea informally to maybe guide your plans. Right, you might say, okay, if I get a 0 over 0, if I hypothetically were to do a plugin thing, that kind of makes me feel like I'm going to be looking for getting a factor that I'm going to divide out from the numerator and denominator. Or if I get like an infinity minus infinity, maybe I have to get that all under one fraction and work with that. Or maybe I have to do maybe two different cases, like approaching from the left versus the right, something like that. Another property, another theorem that we can use in some cases is called the squeeze theorem. It's maybe a little bit less of a hugely important tool um, for finding limits like these, but there are cases throughout the Calc 1 through 3 course sequence that this idea is going to come in super handy. So particularly maybe like near the end of Calc 2, this idea is really important for things like certain laws that apply to series, kind of infinitely long sums, basically. So, we're introducing the theorem here because it is kind of part of this material. It might be of limited importance for the time being, but later on um, it, it, it does have some important roles. And this is the idea of the squeeze theorem. If we have three functions f, g, and h, where for x near a, near some value, f of x is less than or equal to g of x, which is less than or equal to h of x. So in other words, if I have a particular value a here, and if I have, maybe let's do like green on top. So if I have like f of x, that's going to be h of x on top, h of x on top. If I have another function g that is below h, and another function f, maybe it crosses over here, but near a, it behaves. So near a, if I just look at some little slice of the inputs that are near a, I see that I have f less than or equal to g less than or equal to h. If I also satisfy the criterion that limit x goes to a f of x equals limit x goes to a h of x, that those are equal to some limit L. So if I also have that, so say this is f of x and this is L here, the output L, I notice that the limit x goes to a of f of x is L, and the limit x goes to a h of x is L. Now remember, g is stuck between the two. It's kind of squeezed between these two functions, where h provides like an upper bound, f a lower bound, and as we get closer and closer to a, they, roughly speaking, approach the same point. I mean, they could be one of these edge cases where it's not defined at a or something like that, but the limit exists in as L. If I'm going to draw a function g satisfying this criterion between functions f and h satisfying this criterion, it's like, I mean, it can do crazy stuff over here, but near a, it's got to settle down enough. It's got to stay between them. It can't be, in a sense, too poorly behaved and to not have a limit, because f and h are, nicely behaved enough to have a limit. And if it has a limit, it can't be anything other than L, because the limits of f and h are L, and g is between those two. So, the limit of g has to be between L and L. It's got to be L. I think the statement that if the limit of g exists, then it has to be L is, I think, pretty obvious, pretty clear. The idea of why should it be true that the limit of g has to exist, that it can't like wiggle around infinitely fast or something as it kind of moves in towards a. That might be a little bit less obvious and a little less clear. We're not going to go through a proof of the squeeze theorem, but I just do want to point that out, that we are really saying two things here. we're actually claiming that the limit of g exists and that it equals L. So we're really doing two things. We're saying that this limit exists. I mean, if we didn't know anything else about g, the limit might not exist. But under these criteria, the limit of g exists as x goes to a, and it equals L. So this is really saying two things. The limit exists, and it tells us what the limit is. Okay, so let's look at two examples. One of these we've seen before. We investigated with the calculator, but now we have a different tool. We're going to see that there's a nuance that pops up in the second one. So let's take a look at the first one, which avoids that nuance. So here I have a function. This is the function I'm interested in. This is the function I want to know what its limit is. So I'm going to name it g. G of x is x squared times sine 1 over x. And an important detail about the sine function is it is strictly, well, not strictly, it's between -1 and 1, including the endpoints. It's restricted in the size of its outputs. I also noticed that x squared is always positive and x squared is strictly positive when x is not 0. So x squared is strictly positive. The sine function is stuck between -1 and 1 inclusive of the endpoints. Well, that means that the biggest that the sine function can be, the biggest its output can be is +1. So which order did I have these up here? Okay, I had green up top. The biggest the sine function can be, the biggest its output can be is 1. So the biggest that the g function can be is x squared. So if I come over here and draw a picture, I have my function y equals x squared here. This is my h of x function. This is my upper bound function because g has to be less than or equal to x squared. Now on the flip side, the smallest that the sine function's output can be is -1. So the smallest the g's output could be is -x squared. Let me fix my coloring on my g. So I also have this function y equals -x squared looking like this. And I'll call this f of x because it's the lower bound on g. And what does g look like? Well, it does something, it wiggles around a bunch, but it's always stuck between these two functions. So I have f less than or equal to g less than or equal to h, really everywhere in this case, but certainly near 0. Everywhere but at 0, because at 0, the sine 1 over x is undefined. I have a second criterion that I need to satisfy to use the result of the squeeze theorem. What is limit x goes to 0 of f of x? What's limit x goes to 0 of -x squared? Well, f of x is just a polynomial. The corollary says I can do the plug-in property, just plug 0 into -x squared, and I get 0. But that's also limit x goes to 0 h of x for basically the same reason. H is just x squared polynomial through the plugin property, get 0. So my functions line up in the desired way for the squeeze theorem, and the limit of the lower bound function, limit of the upper bound function are the same. Therefore, by the squeeze theorem, limit x goes to 0, g of x, number 1 exists, and number 2 is equal to that same common limit, 0. Any questions so far in this? Okay, let's look at this next example. Does the exact same analysis work for this next example if I just swap in x instead of x squared? At first glance, it seems like it does. Let's be really careful though. So again, let's go through and we'll say that we're going to call this g. Again, I know that the sign bit is between -1 and 1 inclusive. However, this x piece here is not necessarily strictly bigger than 0. So what does that mean? If I tried to do something similar up here, if I tried to look at if I try to look at this and make a claim like negative x is less than or equal to g less than or equal to positive x, if I try to make such a claim, basically saying that the smallest sign can be is -1, so then negative x is the smallest that the output of g can be, and the largest sign can be is +1, so the largest the output of g can be is positive x. What went wrong here? Or did something even go wrong? Well, positive x, y equals x, looks like this. This is what I'm claiming to be h. This is what I'm claiming to be my upper bound function everywhere. And y equals -x, what I'm claiming to be f, I'm claiming to be my lower bound function everywhere. We see that idea works well on the positive side of things when I have positive inputs, but when I have negative inputs, that's reversed. And if I take any open interval about 0, I'm going to be getting a bit of the side where it works and a bit of the side where it doesn't work. So I can't save the day by just saying, oh, well, we're taking a limit going to 0, just stick close to 0. I'm always going to get a bit of the side where the upper function is where it's supposed to be and the lower functions where it's supposed to be, and a bit of the side, the negative side, where that doesn't work right. So I really have two possibilities here. I have at least two ways that I can think of to move forward with this. One is to split it into two problems. I can look at the right-hand limit and by essentially the same analysis as up here on the right-hand limit, just swapping in x's for x squareds, I get that the limit has to be 0. And then I could do the left-hand limit. But here, for my left-hand limit, -x will be my top function. So -x is going to be bigger than or equal to g. And positive x, I'm kind of drawing over it in a squiggly line so you can kind of see. Positive x will be my bottom function. So I can make this swap and then proceed essentially along the same lines of argument, just taking the function h of x equals -x to be the upper function and f of x equals x to be the bottom function. And I would get 0 here. Now I've shown that the left and right hand limits both exist and equal the same number, the overall limit is 0. There will be one approach. That there's nothing wrong with that approach. I think that's a fine approach. I'm going to reverse here a little bit because I want to get rid of those squiggles. There we go. The other approach I could take is I could take my upper function to be, oops, one note trying to be helpful. I could take my upper function to be y equals absolute value of x, and my lower function to be y equals negative absolute value of x. I have some absolute values to mess with, but now I can knock the whole thing out without having to go to one-sided limits. And I can take limit as x goes to 0 of absolute value functions just fine, no problems there. Remember the issues that we had with absolute value functions that we saw before were like trying to find a tangent line at that absolute value point, or dealing with secant lines. But we're not dealing with any secant lines or tangent lines or anything here. We're just dealing with just the limit of the functions. So this is probably the more elegant solution. This is kind of the sledgehammer that will definitely work. Either way is fine. But there is this little nuance that we have to be careful. Just because one factor in a product gets bigger, that doesn't mean the result of that product gets bigger. Right? If I'm in debt and then I say I got twice as much in debt, that's a bad thing. So any questions on that? I'm not going to go through all of the details here. The details, either if you do the one-sided limits or the absolute value deal, will look basically the same as the details up here. But we just have to be careful with this little nuance that because this x is able to be negative, we have to be more careful with when we're saying we have an upper bound versus a lower bound for g. Okay. If there are no questions on anything up to this point, we'll jump into the next section then, 2.4. All right, so the precise definition of a limit. Again, this is really kind of towing the line of real analysis or theoretical calculus or advanced calculus. This would be one of the introductory ideas in such a course, and that's why we're kind of discussing it here. But talking about what exactly do we mean when we say the definition of a limit? We kind of had this, we can make the output as close as we like to L by making the input sufficiently close to A, but what exactly do we mean there? So let's define what we mean by this notation. Well, first, we'll consider that f is a function defined on some open interval containing A, except possibly at A. It's okay if it's not defined at A. In other words, there exists an open interval C to D such that A is in the interval C to D. And if we take the open interval C to D, remove the single point A from that interval, that's a subset of the domain of F. So every point in that open interval, remove A, every other point is in the domain of F. Then we say the following. We say this notation, limit x goes to A, f of x equals L, a real number, means the following. This is the so-called epsilon delta definition of limit because it uses epsilons and deltas. You don't have to use epsilon and delta, but everybody does, so it's always written this way. For every epsilon bigger than 0, so no matter which value of epsilon that's positive you choose, the following is true. It's not stated as such in the definition, but we typically think of epsilon being quite a small number. The following is harder to show for smaller numbers epsilon. So we think of epsilon being a small number. If it works for a small epsilon, it's going to work for a big epsilon. So for every epsilon bigger than 0, there exists a delta bigger than 0. We can find a value of delta for which the following is true. So given epsilon, we can find delta. That means delta can be and typically is a function of epsilon. Given epsilon, we can find a delta. That delta is typically going to depend on which value of epsilon you choose. So for every epsilon bigger than 0, there exists a delta bigger than 0 such that the following is true. If absolute x minus a is strictly between 0 and delta, what does this mean? Well, the left inequality, absolute x minus a bigger than 0, that really just means, this means x not equal to a. So remember, that was that part of the, by choosing x sufficiently close to a, but not equal to a, that's this piece here, this absolute x minus a bigger than 0. And absolute x minus a less than delta means negative delta less than x minus a less than delta. Or that means that x is between a minus delta and a plus delta. X is close to a if delta is small. Delta depends on epsilon, so if epsilon is small, delta is probably going to depend on it in a way that it is also small. Okay, so what do we have? For every epsilon, there exists a delta bigger than 0, such that absolute value of x minus a being strictly between 0 and delta, or in other words, x being not equal to a, and within delta units of a, that implies that absolute value of f of x minus L is less than epsilon, that the absolute value of the output of the function for any of these inputs in this small interval around a minus L, the hypothesized limit, is less than epsilon. So what am I saying? I'm saying basically in mathematical symbols what I said in words above. I can make the output of f as close as I like to L within epsilon units of L for whatever epsilon you choose. It could be 1 or 0.1 or 10 to the minus 10. I could make the output of my function that close to the claimed value of the limit by choosing values of x that are sufficiently close to a within delta units of a, but not equal to a. So this really is, I mean, what we said in words really is pretty precise. We just made it very clear exactly what we mean by that. This is kind of just putting those words into mathematical symbols so that it's very clear precisely what each of them means. So practically speaking, if I want to use the definition of the limit to prove that the limit of a certain function at a certain point is L, practically what that means is I say, okay, given an epsilon, I will tell you what formula to use for delta as a function of epsilon. And then I will demonstrate to you that this implication is true. That if this is true, then this is true. That's practically what it looks like to prove uh, the value of a limit. We're going to start maybe one step back from that, and we're going to illustrate the definition of a limit graphically. And we're going to use this as the limit that we'll work with. Limit x goes to 2 of x squared equals 4. So this is my claim. Can I illustrate what's going on here using a graphical technique before we get into all of the algebra, which can be a little more abstract? So what do I have? I have a function x squared I'm interested in what happens at the point 2, x equals 2. I'm looking for the limit as x goes to 2 of x squared. And my claim is that it's 4, that the limit is 4. Now up here, I'm saying for every epsilon bigger than 0, so let me pick an epsilon. Maybe I'll start with an epsilon equal 1. What purpose is this epsilon serving? It's telling me how close my outputs have to stay to my limit. And let me actually zoom this in a little bit. So this will be 1 unit up, or going up to 5, and 1 unit down, or going down to 3. So if my desire is to stay within 1 unit of L of 4 for any output of my function, f, how do I have to restrict my inputs? Well, what do? I follow this over to my function, down to my input space, and I see that the output of 3 is related to the input square root of 3, right? Square root of 3 squared is 3. I also see, maybe I'll do this in a different color. I also see that the output of 5, if I follow this over, and then down to the input space, I see that output of 5 is related to an input of square root of 5. Square root of 5 squared is 5. So to keep my outputs within 1 unit of 4, keep my outputs between 3 and 5, I have to choose inputs between square root of 3 and square root of 5. So for epsilon equals 1, well, my inputs have to be restricted to square root of 3 to square root of 5, and I probably should have open parentheses here because I have strict inequalities up there. What does that translate to in terms of a delta? Because that's really what I need to find, is what is the delta? Well, let me bring up, this was one of the windows I closed, but let me bring up a calculator again. Recombobulate my windows here because I closed everything because it wasn't working. Okay, so what is square root of 3? Let's do just square root of x. And what's square root of 3? I'm just going to use it as a calculator like this, about 1.73. Up to square root of 5. What's square root of 5? About 2.24. So in other words, on the upper end, this is like 2 plus 0.24. So if I have a delta of 0.24, the right-hand side will be happy. 1.73 is like 2 minus, well, what's that? That's going to be 0.27. So if I have a delta of 0.27, the left side will be happy. I need to pick a delta that makes both of them happy. So I could pick, for instance, pick delta equals, say, 0.24. And that will give me a slightly tighter left endpoint and a right endpoint that's right at where I need it to be. If I restrict my inputs to this interval, then my outputs will be restricted to this interval 3 to 5, or my outputs will stay within 1 unit of my hypothesized limit. Now, here's the important thing. I can really basically do this for basically any function. But the important thing is we did this for one epsilon, but this has got to be able to be done for every epsilon bigger than 0. So let me come over here and kind of redraw this picture. I'll try to make it a little bit bigger too. My OneNote is just really acting up on me today. Uh, this morning it was my allergies acting up, and now it's my computer acting up. Okay, so now let's look at this kind of for an arbitrary epsilon, for a fixed but arbitrary epsilon. So again, I have 2 here. I have 4, which would be, I suppose, like roughly there. This is my claimed value of the limit. And now for a more general epsilon, I'm going up to 4 plus epsilon and down to 4 minus epsilon. If I follow those, so I'm looking to restrict my outputs to this interval 4 minus epsilon to 4 plus epsilon. If I follow those most extreme outputs over here, I see that on the right-hand side, an output of 4 plus epsilon corresponds to an input of square root of 4 plus epsilon. And an output of 4 minus epsilon corresponds to an input of square root of 4 minus epsilon. This left-hand side is always going to be a little further away from 2 than the right-hand side is. So I can get the desired constraint on my output being within epsilon of 4 for all of my outputs, as long as I choose inputs that are in this open interval here, or that is from root 4 plus epsilon, 4 plus epsilon on the right-hand side. And if we just name this delta, delta will be root 4 plus epsilon minus 2. The left-hand side will be 2 minus delta. All right, so any questions on that? So this is the idea that we're trying to get at here, is that I can do this for any epsilon. Now, it's actually super important that I've leveraged here that this is an increasing function. It's not a function that, like, if my function did something like this, well, then I wouldn't be able to just look at the 2 endpoints. I'm making heavy use of x squared being a pretty simple function to illustrate the point. So that is an important note here, is kind of the process that I've applied here doesn't work for every single function out there. I'm making heavy use of the nature of the x squared function here. But I think this is a great way to illustrate the point. And again, at this level, we're not looking to exhaustively analyze all of these definitions of a limit and so on. We're looking to just get an idea of what's going on under the hood, so to speak. Okay, let me switch back to this screen share. think I can close this window. And sorry, I'm just rearranging my windows here. Just give me 1 second. Okay. All right, so let's move on to the algebraic side of things now. We're going to try to take this idea and kind of write it out algebraically. So let's try to prove using the definition of a limit that this is true. In other words, what we want to prove is given epsilon greater than 0, we want to say let delta be something. We're not sure what yet. Up here, we found delta to be, this thing that seemed to work. But the thing we choose for delta is going to depend on what function we're using, what value we're limiting to, and so on. And then we want to show that absolute x minus a between 0 and delta implies absolute f of x minus L less than epsilon. So that's the structure of these proofs. I start off by saying given epsilon bigger than 0, it's an arbitrary positive number, but at this point it's fixed. I can define delta on the basis of that epsilon. So delta will typically be a function of epsilon. I'll typically need to do some scratch work off to the side to figure out what I should choose delta to be. What would be a good choice for delta? That's, a little bit like what I did over here, doing some analysis to figure out that root 4 plus epsilon minus 2 is a good delta to use here. And then I want to go through some steps to show that if absolute x minus a less than delta, then absolute f of x minus L less than epsilon. Okay. So that's the structure that we want. Let's start writing it out. So we'll say let epsilon bigger than 0 be given. And here we're just going to actually, we're just going to choose delta, which remember is a function of epsilon. We're just going to choose delta to be epsilon. It turns out that'll work for this problem. We're going to leave the figuring out what delta should be to a future problem. That's kind of the trickiest part. So we're just going to work through a basic proof right now. And then I want to show this. Keep in mind, f of x equals x and L equals a. So since I chose delta equal epsilon, then 0 less than absolute x minus a less than delta implies, what does that imply? I wanted to imply something about absolute value of f of x minus L. What is f of x? It's just x. What is L? L is just a. So what does this imply about absolute value of f of x minus L? What does my assumption say about absolute value of x minus a? Well, that's less than delta directly from the assumption, but I just chose delta to be equal to epsilon. So that's less than epsilon. So we've shown that if I choose x within delta of a, but not equal to a, then the output f of x equals x differs from L, the limit a, by at most epsilon. And I chose my delta to just be epsilon. That turned out to work just fine in this case, basically because f of x minus L just turned into x minus a, which is exactly what I have here. So this might be maybe the easiest non-trivial limit to prove. This was one of our limit properties, right? Limit x goes to a of x equals a. Okay, let's look at this example. Prove using the definition of the limit that limit x goes to a of c equals c. Again, let's kind of think of the strategy here. What's my goal? I'm gonna let epsilon bigger than 0 be given. So epsilon is some fixed positive number. It's an arbitrary positive number, but it's fixed now. And I'm going to choose a delta. It could be dependent on epsilon. I'm not sure how I'm going to choose it yet. So I'll leave that blank for right now. And I want to say then, zero less than absolute x minus a less than delta implies, what do I need here? F of x minus L. But wait, f of x, that's the function that's inside the limit, is c. And L is the value that the limit is equal to. F of x minus L is just c minus c. But c minus c is just always 0. And epsilon has to be a positive number. So 0 is certainly less than epsilon. I could choose delta basically any way that I want. It just has to be positive to satisfy this inequality. I would choose delta to be, I suppose I could choose it to be epsilon or square root of epsilon or epsilon over 2. I just choose it to be 1. Doesn't really matter. So I could pick delta to really be any positive number that I like. Could be a function of epsilon. It could be not a function of epsilon. It just has to be strictly positive. Then 0 less than absolute x minus a less than delta implies absolute f of x minus L, which is just equal to absolute c minus c, is just equal to 0 all the time. And that's less than epsilon because epsilon has to be strictly positive. So we've proven another one of our limit properties, that the limit of a constant function is that constant value. Okay, now let's look at kind of a non-trivial limit. This is the last example we're going to do here. And this is, kind of the upper end of the difficulty that we're going to look at in terms of these limits. You can see that this is not the limit of a particularly complicated function. It's just a linear term and a constant term. But we want to prove the value of this limit. Now we do have that corollary that says, well, this is the limit of a polynomial. We can do the plug-in thing. 2 times -4 is -8 plus 10 equals 2. So that's why I think that this is the correct value for this limit. Importantly, when I'm going through these limit proofs, I need to kind of have a limit in mind that I'm trying to prove. So I don't go through this epsilon delta definition to figure out what I think the value of the limit is. I say, I think the value of the limit is this. Here's my proof. So again, what's my kind of goal here? I want to say something like let epsilon bigger than 0 be given. At this point, epsilon is a positive number that's arbitrary, but it's fixed. I want to choose delta to be something. Again, I'm not sure what yet. I'm suspecting it's going to be a function of epsilon. And I want to say then 0 less than absolute x minus a less than delta. Again, kind of in words, what does this say? On the left-hand side, it says x not equal to a, and the right-hand side says x is within delta distance of a. That implies absolute value of f of x minus L, well, that's 2x plus 10 minus 2 less than epsilon. Oh, and that shouldn't be x minus a. I know what a is. A is negative 4. So x minus a is x minus a negative 4. That's x plus 4. So how do I choose my delta now? This is really the big question in all of these limit proofs. Well, really what I want to do is I want to take the conclusion that I have in mind. I want to massage it. I want to work with it algebraically and try to make it look something like, I want to make this inequality look something like absolute x plus 4 less than something. If I get absolute x plus 4 less than something out of this epsilon inequality, whatever that something is, I pick that to be delta. And then I basically reverse the order of the steps and write out the proof. So I'm going to reverse engineer this. I'm going to come off here to the side, some scratch work, and I simplify this. I get absolute value of 2x plus 8. I want to be less than epsilon. And I'm looking to work my way down to absolute x plus 4 less than something over here. This is my goal. But nicely enough, 2x plus 8 has a factor of 2. That factor of 2 can come out of the absolute values and divide through. Oh, help if I did my basic arithmetic right. X plus 4. This factor of 2 can divide out, give me absolute value of x plus 4 is less than epsilon over 2. So if I choose a delta such that absolute x plus 4 is less than epsilon over 2, I can reverse this process to get exactly the conclusion that I want. Okay, so what does my proof look like then? Let me erase this bit. So I've decided that I want delta to be epsilon over 2. So we're going to choose delta equals epsilon over 2. Then we can say 0 less than absolute x plus 4 less than delta implies that 2 absolute x plus 4 is less than 2 delta, but that's just epsilon. This implies that absolute value of 2x plus 8 is less than epsilon, implies that absolute value of 2x plus 10 minus 2 is less than epsilon, or in other words, absolute value of f of x minus L is less than epsilon. And we've proven our limit. this way. We can make the output of 2x plus 10 as close as we like to the limit of 2 by choosing inputs sufficiently close to -4. And specifically, if I say that I want the output of f to be within epsilon units of 2, I should choose inputs that are within epsilon over 2 units of -4. That kind of makes sense because my input kind of gets stretched by a factor of 2 moving to the output. So that's where this factor of 2 comes from this factor of 2. So it's kind of sensible. Now, again, like this is a pretty straightforward function. Are we going to be doing this, for the rest of chapter 2? Well, no, we're going to leverage some of these properties. We proved a couple of the properties here. Some others of the properties, we could prove, but we're not going to go through all of them. And some others of the properties, we would need to develop more mathematical tools in something like a theoretical calculus course before we'd be able to prove those. But we're going to be using the properties that we outlined way back at the beginning of the lecture, along with some other properties that we're going to build up, like this corollary, like the squeeze theorem, like some stuff that we'll see in the next couple of sections. We're going to use all of that. So we're not going to be using the precise definition of the limit in every problem from here on out, but I think it is important to understand a little bit about kind of what's going on under the hood here. When we take a limit, what do we actually mean? I think it gives a deeper understanding. And I'm kind of the philosophy that, at least for myself, and I think this applies to most people, is like you only understand like one layer less deep than the deepest you've gone. So, like whatever coursework you've taken, you probably like actually understand like one course below the maximum course that you've taken so far, or same idea here. If we go kind of under the hood a little bit, it helps us to understand things like why is it so important that we like not plug in, not just through the plugin thing automatically. I think I've given enough counterexamples, but we can see in the precise definition of the limit here, that is one of the pieces of it. So when we say the limit is this is exactly what we mean. And one of the criteria is that x is not equal to a. All right, any questions from anything we did today?